Hi, Year 12s. So now on to subtopic 2.2, equilibrium and yield. Now, the first part will be looking at equilibrium. Now, equilibrium is when a chemical reaction that is happening reaches a point at which there is no more change in the concentrations of the participants in the reaction, or the chemicals that are involved in the reaction. Now, let's get the laser pointer ready. Now, it says here, first of all, that chemical systems may be open or closed. And apparently, there you go, the laser. If they are open, that will mean that, if a reaction's happening, some of the components can be lost to the environment, and they don't take part in the reaction anymore. Instead, when it's closed, you have a sealed container. All the components of the reaction are still in the same place, so they can all take part in the reaction still. We are looking more at closed systems because they are things that can reach equilibrium. Now, we've got to start with, we've got two graphs, so number 1 and number 2. They're both illustrating slightly different things, very similar but slightly different. Now, what we see here is a concentration over time graph. So as the time goes on, our concentration is changing of the components of our reaction. Now, for this particular one, we see our reactants. So we start with some amount of reactants, and it is decreasing over time and eventually ending up flat. Now, conversely, we have products which started off as a lower amount, and it's increased until it reaches a flat point again. Now, we can see, just like with the reactive reaction, our slope is the greatest at the start because our reaction rate is the greatest at the start. Eventually, our reaction slows down to essentially nothing. So that's when we have our flat lines of our concentrations. So there's no change over time anymore. So if you are trying to illustrate a reaction and it tells you at a certain time the reaction has reached equilibrium, your graph that you draw should be flat at that point and then onwards. Now, just to be really clear, I mentioned in rates of reaction, this point just here, the reaction at equilibrium has not actually stopped. The reaction is still happening, both forwards and backwards, but both those reactions are happening at the exact same rate, so that we have no overall change in our concentration of our reactants and our products. So one way to just explain it, at the start of this reaction here, you've got lots of reactants. When you've got heaps of them or high concentration, they're going to react faster. And when they react, they're going to form our products faster. Now, as the concentration of our reactants decreases, we're making the products less quickly. So we're getting those increasing less quickly. Now, similarly, those products are increasing in concentration, so they are going to react themselves back into the reactants, and that rate will increase as the concentration increases. Eventually, we get our reactants getting to a point where they are forming products at the exact same rate that the products are forming reactants again, and that's when we have equilibrium, where there's no net change. So number 1, so this first one here, we see an increase in our product concentration and a decrease in our reactant concentration of roughly the same amount. So if we look at this amount that it's increased and that amount that it's decreased, they are pretty much the same. Number 2, on the other hand, we see our reactions decreasing by a certain amount, so about this much. Our products, on the other hand, increase by a smaller amount. And in this case, I was trying to illustrate half as much. Still, otherwise the same trend happens. We have our fastest rate of decrease of reactants, our fastest rate of increase of products at the start. They will reach equilibrium at some time, and the concentrations of them do not change anymore. The slope is 0. For number 1, that would be a reaction such as this, where we have A plus B goes to C, where the ratio of reactants, so A to C is 1. Similarly, B to C is also 1. So it wouldn't matter what we're plotting. If we're plotting the reactant A versus the product C, or B versus C, we would see the same thing. Now, on the other hand, graph 2, where we see the ratio, so the decrease of our reactants, the amount it decreases, the amount it decreases is twice as much as the increase for the products, it would be a reaction like this where we have a stoichiometric ratio of 2 to 1. For every 2 reactants we lose, we're only gaining 1 product. So this is going to decrease twice as fast as the product's concentration increases. And that's pretty much it for those concentration time graphs. So moving on to the next part, which is something called equilibrium constant, or KC. So I'm just going to add in. Now, KC is what we call the equilibrium constant. So we have that just here. And it is the ratio of the concentrations of reactants versus the products of reaction. Now, specifically, that is only when at equilibrium. So once the reaction has stopped changing the concentration of our reactants and products. Trying to get this thing, there we go. Laser's working now, good. When the reaction has stopped changing, that's when we can calculate this equilibrium constant. So for this particular generic reaction, which is A and B make C and D in these particular ratios, so we have A, B, C, and D as the stoichiometric coefficients, we can make an expression that shows us the ratio of products, the ratio of reactants and products. More specifically, it is equal to the concentration of our products multiplied by each other, raised to the power of their stoichiometric coefficients. So in this case, we have the concentration of species C raised to the power of its stoichiometric coefficient lowercase c, and multiply that by D with its stoichiometric coefficient as its power. So if lowercase d was a 2, this would be squared. If it was a 1, it would just be leaving it as it is. Now, so that's the products, and the reactants are essentially exactly the same. So we're dividing products over reactants. All the components are raised to raised to the power of their stoichiometric coefficient. Now, an important point to note is this value is going to be constant for a reaction. So a particular reaction is going to have a certain Kc value, and that will be a constant value as long as the temperature of the reaction stays the same. So if the reaction temperature is constant, the Kc value will not change. Often they're going to, so in the questions that you'll get in tests and exams, they will say, you're assuming that the temperature does not change, so that the Kc value is constant, even with, so that when we change a concentration of a product or reactant, we know that our Kc value will stay the same, and we can adjust all the other components, as you'll see in a minute. Okay, so here, as I said, like that, the Kc value doesn't change. So if we mess with any of these parts, so any of these parts here, it is going to make the other ones change, so that Kc value stays the same. You get a lot of practice with this. Now, when we see the Kc value itself, the number will tell you, whether a reaction favors forming products or favors forming reactants. If you see a value, so first of all, Kc can't be less than 0, because there's no way this ratio here can be 0. It can be greater than 1 or less than 1 though. So if it's a really small number, that means our reactants here, so really small as in close to 0 or much less than 1, that means our denominator, our reactants, is a much larger number than our product at the top. Conversely, if we have a very large number, that means our numerator at the top is much larger than our denominator, and so our product concentrations at equilibrium will be much higher than our reactant concentrations at equilibrium. Now, we know that with equilibriums, with these things here, we can actually change the direction that we write these reactions. So forward and backward is just whatever we decide them to be. So if we do swap it, it will swap this Kc value. It'll invert it. It'll swap the top and bottom of it. So in this reaction up above, A and B are our reactants, C and D are products. If instead we make our A and B our products and C and D our reactants, we'll just flip this whole thing over, and that will invert our Kc value. So a value of Kc that's really large will become really small, and a Kc value that's really small would become really large if we were to swap them around. Now, you are going to be asked at some point to calculate Kc, and you will be given, hopefully, or you will definitely be given enough information to work out the concentrations of each of the components of the reaction. You could also be given Kc and maybe a couple of components and be expected to find an unknown concentration. So you should be able to rearrange this, and the maths involved is straightforward. To get, for example, this concentration over this side, you'd multiply both sides by that value. Now there is another value that is related to equilibrium constant, and it's called the reaction quotient Q. Now, the expression itself, so the mathematical expression, so this here, for example, is a mathematical expression. Once it's circled itself, there we go. That is a mathematical expression. Kc is the value when all of these, when the reaction's at equilibrium and we have these concentrations. But we can chuck in these values at any time of the reaction. So, for example, at the beginning of a reaction, we can find out what Q is. We can find out what this expression is. But if it's not at equilibrium, we call it Q instead. So it's a reaction quotient. It looks the same as it says here, it's the same form, but its value will not be constant. It'll be different at every time. And you can compare it to Kc to see what the reaction is going to be doing at that moment. So for example, if Q is much larger than Kc, that means that the reaction is going to change so that Q drops down to meet Kc. And so we need to decrease the number of products and increase the number of reactions. So if we go back up to here, if Q is large, that means we have a lot of larger than Kc. We have too many products and not enough reactants, so the reaction will go backwards. So decreasing the products, increasing the reactants, so we're going backwards. Now conversely, if Q is smaller than Kc, that means Q needs to increase for our expression to reach equilibrium. And so what we'll see is, apparently I didn't even finish off what I was writing there. So that will increase the concentration of products and decrease reactants. So this will make the reaction, so the reaction will be moving forwards after this point in time. Okay. Now, when we're doing these sorts of problems, there's a way we can, a method you can use to sort of work out all the values relative to each other for a particular reaction. And this table here is what we use. So it's called an ICE table, ICE. So I stands for initial concentration of our substances or our chemicals in our reaction, or the chemical species. C is the change in concentration that occurs over the course. So once we start our reaction, things are going to change to reach equilibrium, and what that change is, we need to fill out. And our equilibrium concentration, our final concentration, will be the thing we're most concerned about when we're thinking about working out the equilibrium constant value. So what I'll do is I'll get my pen out. On my computer, I've got a calculator because I am pretty sure I'll be needing it. Now, this particular reaction we're looking at is carbon dioxide reacting with hydrogen to form methanol and water. Now, we're given a few values. So we're given the initial concentration of our carbon dioxide. The concentration is in moles per litre, it's 0.20124. And we have our final concentration, our equilibrium concentration. Once the reaction has stopped happening, we get 0.20000. Now, what you can work out from here directly is the change, and it is, in this case, it's dropped, so it's negative 0.00124. So we've dropped by that amount. It's quite a small amount. Now, the important bit here, what I'll do is I'll keep it simple, is if we decrease the concentration of this reactant, the only way for that to have happened is for our reaction to have proceeded forwards. If we use up our reactant we are going to gain products. Now, what we need to look at is the stoichiometric coefficient of the CO2. There's an invisible 1 in front of it, and that matches the stoichiometric coefficient of the methanol, CH3OH, and the stoichiometric coefficient of water, H2O. That means for every change in our CO2, so for the concentration change in our CO2 will equal the concentration change in our methanol and our water, but opposite in sign. Because if we're losing our reactant, we're gaining our product. That means this will be plus 0.00124, and this will be plus 0.00124. Both of these will increase by the same ratio, because the stoichiometric coefficients are the same. Now, if we started with 0 of our methanol and water, then this should be fairly straightforward. We end up with 0.00124 because we increase from 0 to by that much. Similar, exact same thing for this one here. Now, the only one we may need to just quickly use a calculator for is our H2. Now, for this reaction, for every mole per liter, for every unit of concentration our CO2 decreases, we need 3 times as much hydrogen. That means its concentration is going to decrease by 3 times as much. So instead of a decrease of 0.00124, we will have 0.00124 in my calculator. I'll times that by 3, and that will give me a decrease of 0.00372. So this is the reason why I need my calculator. And if I have a final concentration of 0.10000, that means I've gotten to that value from some value that was 0.00372 higher. So I'll need to add those two together, which will give us 0.10, just double checking, 372. Yep, there we go. So now what we've done is we've used the information about this reaction. The information given to us about the values of the reactants and products at equilibrium or at the beginning of the reaction. And we've used the stoichiometric coefficients, the values in front of each of these, to work out how each of them would have changed. So now that we've done that, if we wanted to, we could work out the equilibrium constant. Now, I might as well actually just give that a go. So while I'm here, I'll use my red pen, and I will make the expression. So Kc will be equal to the products, so the concentration of our CH3OH. Now remember that's a gas, and the power here is going to be 1 because the stoichiometric coefficient is 1. I'll multiply that by the concentration of our water in gas form to the power of 1, because its stoichiometric coefficient is 1. And that's going to be divided by our CO2 concentration to the power of 1 again, multiplied by the H2 gas concentration raised to the power of 3, because it's got that 3 in front of it. Now, just so you know, that power of 3 is, oops, that's not what I wanted at all. Let's go back. It's raised to the power of 3 because you can think of this reaction as being, I'll erase this afterwards, but you can think of it as being CO2 plus H2 plus H2 plus H2. And so if we did our reactants multiplied by each other, it would be concentration of CO2 multiplied by the concentration of H2 multiplied by the concentration of H2 multiplied by the concentration of H2. And so because we have 3 of them, they're multiplying by each other 3 times. And so we simplify that down into H2 to the power of 3. Now again, I'm going to remove this because not expressly necessary, but that's where it comes from. That's why we have that power raised. Because if we have 3 of a component, we're just adding 3 of them, and we treat them the same as every other component. So what you would do for this particular one is you are going to put in these values here into this expression. Oops, sorry, that's not what I want. I don't want that plus there, that's not necessary. So we put all those values into here, making sure that we take that 0.1 and raise it to power 3, and that will give us our equilibrium constant for this reaction. If you were to have attempted to work out what Q is at the start of the reaction, it would actually be 0 because the concentrations of our products are 0, but obviously 0 is less than our Kc value, so the reaction would need to proceed forwards. Okay, so moving on to the next section, we have what's called Le Chatelier's principle. Whether I pronounce that properly or not, I have no idea. Regardless, this principle is a way that we can sort of shortcut recognize or predict what is going to happen to a reaction if we make some sort of change to that reaction. So if we have a reaction happening and we mess with the concentration or the pressure or temperature or some other things, we will have some idea of at least predicting what's going to happen. Now, one thing that's really important is that Le Chatelier's principle is not the reason. So just like what I've said here, it doesn't explain why it's happening. It just allows us to predict what is going to happen. So very roughly, I'm not going to give you the exact definition of it, but the rough definition is whatever changes occur to a reaction at equilibrium, the reaction is going to try and counter that change or reverse that change somewhat. Now, it's never going to reverse it perfectly or all the way back to what it was, but it's going to make some adjustments. So if you for example, let's have a look at concentration, and hopefully it'll make more sense. If we mess with the concentration of a reactant, let's say we increase the concentration of our reactant, as for this example, the reaction is going to try and decrease that back down a little bit, so it's going to make more products form. So it's going to use up the excess reactants that we've added by making more products form. Similarly, if we increase the amount of the concentration of our products, the reaction is going to go backwards, make more reactants to try and undo that change, that increase of products that we did. So now I said here that the Le Chatelier's principle does not explain the change, but here is the explanation. The deal is that reaction rates are affected by the concentration. If you increase the concentration of reactants, that is going to make the reactants reacting together happen more quickly. So you're going to have a net forward reaction to reduce that, which is going to reduce the amount of our reactants, and it's going to make the products increase. Now, once the products increase a bit more and the reactants decrease a little bit, eventually the reaction rates forward and backward are going to stabilize. They're going to get back into equilibrium, and so we get back to equilibrium eventually. If we do increase the concentration of our products, that's going to increase the reaction rate of the products back into reactants. So that's going to make the reaction look like it's going to go backwards. So we're going to decrease the product concentration and increase the reactant concentration. So pressure of gases, it's a very similar deal. So as I said, it's analogous to our concentration for both gases and liquids. Stuff in solution, but pressure is for gases. If you increase the pressure, or you're going to have a faster reaction, similar to if you increase the concentration, you're going to have faster reactions. So the deal for gases, though, is that when you, let's say, increase the overall pressure by squeezing the vessel, squeezing the things down into a smaller space, you're going to get more frequent reactions both forwards and backwards, but each direction is not necessarily going to be affected the same amount. So the deal here is that if you increase, here we go. Le Chatelier's principles say that the reaction is going to move in the direction with the least number of moles of gas. So in the reaction, in that chemical reaction. So if you have 2 moles, two molecules of gas in the left-hand side in the reactants, and you have 3 on the right, increasing the pressure will move it to the left. Similarly, if you decrease the pressure, so you expand the vessel, and so the particles are further apart, it's going to try and re-increase that pressure by making more molecules of gas. So I actually probably didn't actually mention that in the first bit, but if you increase the pressure, the reaction's going to try and decrease the pressure again, and the only way it can do that is by reducing the number of molecules of gas there are in that vessel, and it does that by moving to the side with a fewer number of moles. Now we do have an example down here, and I'll use this example for both the Le Chatelier's principle bit and the actual explanation. This reaction here, we have our stoichiometric coefficients at the front, so we have one of A, one of B, and one of C. In this particular case, on the left-hand side, we have 2 molecules of gas, or the molar ratio of gas is 2 to the 1 on the right-hand side. So 1 plus 1, and then 1 on the right. If we were to increase the pressure of this reaction, the reaction is going to move to the forwards to go to the side where we combine A and B to make half as many molecules of gas. And conversely, like I said before, if we decrease the pressure, the reaction is going to change to increase the number of moles of gas by moving backwards, forming A and B from C. So we take C, which is 1 molecule, and break it up into 2, A and B, so that we twice as many molecules of gas, which will increase the pressure again. Now in blue, we have our explanation. Essentially, when we change the pressure, we are going to be changing the relative rates of the forward and backward reaction, and those relative rates are going to differ. So if we're going to increase the rate as we increase the pressure, but the forward and backward reactions are not going to increase the same amount necessarily. So for this example here, if we increase the pressure, we're going to get A and B reacting together more often, which is going to increase their rate. But in this particular example, C doesn't actually react with anything. So C doesn't really care about the increase in pressure. So its reaction rate, once this computer stops being silly, its reaction rate backwards is not going to be affected, whereas the rate forwards is going to increase, which is going to make more molecules of C, which matches our prediction. Now again, if we decrease the pressure, then that means A and B are further apart, they're going to interact with it less often, and it's going to make the reaction, the forward reaction slow down, whereas C is going to be unaffected, which is going to relatively increase the reaction rate backwards, making more of our A and B. So just as our summary, A plus B reaction is sped up more than the reverse by an increase in pressure, but it's also slowed down more by a decrease in pressure. So that's why we end up with the reaction going forwards or backwards. Now, just by the way, if you have the same number of molecules of gas, so let's say we're making A plus B goes to C plus D, we have the same number of molecules on each side, so the equilibrium will not shift if you change the pressure. The forward and backward reactions both happen faster, but they both happen, they both increase at the same amount. Okay. Now I know there's a lot. Luckily, you can pause and rewind this video. We're on to temperature. Now we did talk about temperature in 2.1. We know that if you increase the temperature, you do increase reaction rates. But the forward and backward reaction rates are not affected the same amount when we do change the temperature. Now, simply, according to Le Chatelier, if we increase the temperature, the reaction is going to move in such a direction that it will try and absorb that temperature change. Reduce the temperature back down. Similarly, if we decrease the reaction temperature, the reaction is going to move in such a way that will release energy to try and make that temperature go back up. So we know that there's exo and endothermic reactions. Exothermic releases energy. So if we reduce the temperature of our reaction, the exothermic reaction, whichever direction that is going to be favored because that will release heat into our system, making it, reducing that heat change or reducing that heat decrease. Now we know exothermic, if an exothermic reaction happens, it's going to make the reaction system colder. So if we heat up a reaction, it's going to prefer the endothermic reaction, which will act to decrease that temperature. So again, that is not the explanation, because Le Chatelier's principle is not an explanation, it's just a prediction. Reactions don't really do things for any particular purpose, but again, it's a tool to use. Now, I do give you an explanation though, whether you need to know it or not, but I've got a little diagram on the left here of an exothermic reaction, which is the forward reaction in this particular case, and we see that the activation energy, so the energy that it takes to get over this over the reaction barrier, is smaller going forward for our exothermic reaction than it is for our backwards reaction from our products to our reactant, which is the endothermic. So endothermic has a larger activation energy than exothermic. So the exothermic activation energy is smaller than the endothermic activation energy, as I mentioned. So if you look at these two, you'll notice that the endothermic needs more energy to overcome the barrier than the endothermic. The endothermic will need more than the exothermic. Similarly, it's benefited more. So the endothermic reaction really needs that extra temperature to overcome the barrier. Whereas exothermic, it doesn't really need as much energy to overcome the smaller barrier. So if we were to increase the temperature, this would have a proportion of molecules with enough energy to overcome the backwards larger barrier will increase disproportionately. So it's this endothermic reaction for an increase in temperature is benefited reaction rate wise much more than the forward reaction is. So think of the forward reaction as not really needing the temperature change. It's already, it's a small value, bit more temperature helps it, but not by that much as a proportion. Whereas endothermic really wants that, extra heat. So any extra heat you give it benefits it a lot. That way, endothermic reactions, if the reaction temperature goes up, it's benefited a lot. It will, you'll get more disproportionate amount going backwards to form our reactants. Similarly, if we decrease the temperature, the endothermic reaction is affected, slowed down more than our exothermic reaction is slowed down. And so we end up with more forward exothermic reactions occurring. So overall, we have an increase in temperature makes our endothermic reaction favored because its speed is increased more than the speed increase of our exothermic reaction. And similarly, our decrease in temperature makes our exothermic reaction favored because it's not slowed down as much as our endothermic reaction is. Now, I know that was a lot of information. Hopefully it made sense. If it doesn't, you know what to do. You let me know as soon as you go through this. Now remember, the textbook also has the same same components. Actually, I should probably double check, but I'm not sure if they give these explanations. I just find they're good for understanding what is actually happening, because that way things tend to make a bit more sense, as opposed to just using a principle, for example. Cool, and good luck.